labs and places like that who are in the field of algorithm development and discovery to appreciate the opportunities and the impact that developing algorithms is going to have. So I'm very much looking forward to hearing from today's panelists, and I will turn it over. I should just introduce myself really briefly. For those of you who don't know me, I'm Celia Merzbacher. I'm Executive Director of the Quantum Economic Development Consortium, or QED-C. QED-C is now about 6 years old. We're sort of a startup ourselves that's growing day by day. We now have about 250 members from around the world. And if you want to know more about QED-C, you can find information, of course, on our website, or you can reach out to us and we'll be happy to answer those. But without further ado, I would like to turn it over to Swamit Tanu with the University of Wisconsin to moderate today's panel. Swamit, over to you.
Excellent. Hi, everyone. Welcome to today's Quantum Marketplace webinar on quantum algorithms. I'm Swamit Tanu, professor at University of Wisconsin-Madison, and I'll be your moderator. The Quantum Marketplace webinars are being recorded, and they will be put on the YouTube channel. So today we'll talk about where quantum algorithms stand and hear from experts who are really shaping this field. Here is what we have lined up. A quick intro to the quantum marketplace, then an overview of quantum algorithms, followed by a presentation from our speakers. We'll wrap up with the panel discussion and audience Q&A. So keep those questions coming through Zoom's Q&A feature, which you should see on your Zoom window. Presenters will provide text responses to the questions as they are able. The Quantum Marketplace is all about giving QED-C members a stage to highlight what they are building and connect with others. These sessions are recorded and shared on a YouTube and the QED-C site. And if you are a member company, make sure your profile is up to date. It's a great way to get noticed. This is a screenshot of QED-C's Quantum Marketplace webpage. You can access it via the link shown on the slide. Or you can click on the Quantum Marketplace tab at the top of QED-C website. You'll see videos posted from past webinars, as well as profiles of QED-C members who provide quantum products or services. QED-C also posts webinars and individual company videos to this Quantum Marketplace YouTube channel, which you can access through this link. All right, so today's topic is quantum algorithms, and algorithms are really the heart of quantum computing. Without them, hardware alone doesn't get so far. Couple of big names you have probably heard of: Shor's algorithm, as it can break cryptographic systems. It can break RSA, but it requires millions of qubits. We want these qubits to be error corrected, so these are extremely complex systems. We will not able to build this thing in a very near term. Then there is a Grover's algorithm, which gives us a nice quadratic speedup for a very general problem of search. So it has a very broad applicability. It can provide some real world benefits, but it's still quite complex and heavy. And then at the end, quantum simulation. This is especially exciting for near-term use because quantum systems naturally model chemistry and materials. And with breakthroughs in quantum algorithms, I think we can quickly show a real-world application of quantum computers, especially for quantum simulation application. And closer to today's hardware, we have got these variational algorithms like variational quantum eigensolver, or VQE, or QAOA. These are hybrid approaches where we mix quantum and classical. They have been tried on optimization, chemistry problems, even on machine learning problems. But the jury still out. Sometimes they beat classical solvers, sometimes not. But by building these applications, we are learning tons of things about systems, about hardware, about which metrics to use. So I'm very optimistic that we will continue to build these applications and learn more things, right? But the big takeaway for today's webinar is hardware gets all the headlines, but the real progress depends on software and algorithms. When building these scalable platforms, we have to think about what are the applications, how to build agile yet general purpose software stack, how to optimize hardware and software together, how to deliver these solutions on a budget, and most importantly, how to retain and attract talent. And to answer some of these questions, we have a panel of 4 experts with us. We have Marwa Farag from NVIDIA, Kenneth Hydrater from qBraid, Travis Scholten from IBM, and Bob Wold from Quantum Rings. Welcome all. They will share their different perspectives from startups to big labs on where quantum algorithms are going and what's the realistic in short term and long term. Please welcome our panelist, and Marwa, you can go ahead and start sharing your presentation.
At NVIDIA, we are not building any qubit, but we are building an accelerated quantum supercomputer. So this is an AI supercomputer that's going to be connected with a quantum hardware, and that's going to be useful for all hybrid application using GPU and QPU. Also, in addition to this quantum supercomputer, we are building a software stack that can be integrated into this quantum supercomputer, because there are going to be several quantum modalities, and we don't know which one will pull on, come first, and also what if there are going to be maybe some of them going to be useful for certain application, other will be for other application. So it's very important to have a software that is hardware agnostic, and we are building software to be hardware agnostic. And that's what I will go through in next slide. We are building the NVIDIA quantum platform, and it starts with CUDA-Q. CUDA-Q is a quantum classical hybrid quantum classical programming model and compilation platform. It's a hardware agnostic. So here you can see all these logos are the quantum hardware that are can be accessed, available in the CUDA-Q backend, including the Amazon Braket, which is a cloud service that enable access for multiple quantum hardware. CUDA-Q is CUDA-like. It's a kernel-based programming model, and it allows tight integration with classical parallel programming as well. Because quantum hardware today is very noisy, and not all of us has access to quantum hardware. So we also see simulation as a very important component for the quantum computing workflow. And at NVIDIA, we also building the quantum simulation library. So this is a GPU accelerated state vector and tensor network, and that's enable user to run their quantum circuit simulation to test it, for example, before running it on quantum hardware. But also it built to help scalability, so user can use the quantum to test their algorithm at a scale that is not accessible today by quantum hardware. In addition to state vector and tensor network, we are also enabled the quantum dynamic workflow. So there is now the GPU accelerated density matrix to enable simulation of the device to help design the quantum hardware. And here on the right, also you can see all the different platforms that has now integrated the quantum in the back end to enable simulation. At the very top, also here in top of quantum and CUDA-Q, we are building libraries to support user with the most important things they want to do with CUDA-Q. And we have two now libraries: quantum CUDA-Q with quantum error correction, and CUDA-Q solvers that is for hybrid quantum classical algorithm. At the very low level, we are building DGX quantum in collaboration with our partner Quantum Machines to enable a low latency interconnection between the QPU and the GPU. And so at NVIDIA, we are building the whole stack, and we welcome everyone to take the part that is more relevant to them, and also leave the rest. So with the quantum supercomputer, user will be able to run a very useful quantum applications, taking advantage of the quantum hardware and AI supercomputer. With the quantum simulation library in CUDA-Q and AI supercomputer, user can start to test and develop their algorithm, and also run simulation as a device, run simulation for the device to design quantum hardware. And we are at NVIDIA, we are collaborating with everyone in the quantum ecosystem. And our mission here is to empower the quantum ecosystem. And we have been enabling that and enabling the most important research, some of the most important research happening these days. And we are proud to help our partner leverage and develop their quantum technology. With that, I thank you.
We can go to our next panelist, and that's Kenneth.
Thanks so much for having me here today. My name is Kenny Heitritter. I'm the VP of R&D at qBraid. We're a Chicago-based quantum computing startup that's aiming to be the one-stop platform for the quantum ecosystem. So I'll tell you a little bit about qBraid today. Obviously, we do a lot of things, but you only get 5 minutes today, so this will be pretty brief. But at a high level, the quantum computing software stack consists of a bunch of different components that are all being developed today. All these components are very incomplete at the moment. People are trying to build orchestration, people are trying to build APIs, people are trying to build runtimes, and also compilers for specific pieces of quantum hardware. Unfortunately, none of these things are quite done right now, and the quantum ecosystem is still at a state where it requires a lot of time and effort to actually get onboarded to quantum computing, to actually run workloads on real quantum computers, even to use simulators or to use packages that are put out by the various quantum computing hardware companies. And so the unfortunate state is that at this early day, the quantum world is still relatively siloed. There's a bunch of different companies that you see here on the screen that all have kind of their own software that's written in their own languages. They're all extremely useful, but they don't necessarily talk to each other extremely well. And it can cause a situation where people who want to explore quantum computing can get locked into one specific component. And so what we try to do at qBraid is to alleviate all of these barriers to moving between these various frameworks, using different pieces of hardware, using different pieces of software. So what we aim to do is to make all these connections that you see here on the screen, giving you a platform that has a single sign-in, single contract, no vendor lock-in, gives you access to all the different quantum compute modalities. And we really think that this is going to be the best way to access quantum computers in the long run. And so our primary offering is something called qBraid Lab, which here you see we offer hosted Jupyter Lab and VS Code instances on the cloud that come with pre-configured quantum software and quantum hardware access. So this includes a range of different pieces of quantum hardware. In this day where AI is gobbling everything up and everyone is using it to write code as well, we also offer both like ChatGPT and Claude-powered instances that speed up quantum development. They have access to quantum-specific documentation, can help users get on board to quantum computing a lot more quickly than they could just by reading the documentation themselves. We also directly integrate with NVIDIA GPUs. So now you can actually go on qBraid Lab, you can start up a GPU instance, and you have pre-configured CUDA-Quantum, Qiskit, Cirq, and we also have all of the common AI libraries like TensorFlow, JAX, etc. And these are all properly configured to work with GPUs out of the box. This also connects straightforwardly with GitHub, allows your developers to use the repositories that already have been building and to share it with other people. And then ultimately you can run on quantum hardware directly from this platform. And then something that's of a lot of interest for a lot of larger organizations is that we do provide a lot of organizational management, which allows you to basically set up which users have so many amounts of credits that they can use for GPUs or quantum computers, and also to stipulate what types of quantum computers, what types of resources people have access to. So this allows you to do a lot of cost control. And so in addition to providing a platform for accessing quantum computers and accessing various types of GPUs and CPU instances and software in the quantum computing ecosystem, we also do a lot of work with partners to try to lead the way when it comes to developing quantum applications, which is kind of the point of what we're talking about here today. And so here on the screen are just a few different things that we've worked on. We've worked on two really cool things with Airbus that are listed right here. We've tried to model metal corrosion using quantum reservoir computing. We've also done some flight trajectory optimization with them. And then we've done some very cool work with Welcome Leap for Quantum for Bio to develop new pipelines for quantum chemistry that could lead to new pharmaceutical pipelines. So you're more than welcome to check out any of these papers if you're interested. And then being a Chicago quantum computing startup, I would be remiss to not say that there's some really cool things going on in Chicago right now. There's something called the IQMP, the Illinois Quantum Microelectronics Park. And as a part of this, we're starting up something called the National Quantum Algorithm Center, which qBraid is really, really excited to be partnering with. We'll be providing the actual infrastructure layer for this quantum algorithm center, allowing anybody who's a part of it to access quantum hardware directly through qBraid. And so through this National Quantum Algorithm Center, there's going to be a series of grand challenges to develop applications of the future that leverage these near and long-term quantum computers. So with all that said, you're more than welcome to get in touch with us via this QR code. Go to qbraid.com or email me directly. Thanks.
Fantastic. Thanks, Kenny. Travis, you want to share your slides?
Thank you, Swami.
Hey, everybody. I was taking a look at the list of attendees. I know some of you out there on the interwebs, so good to sort of see you again virtually. And for those of you that I haven't met, hi, I'm Travis. I currently work as the technical lead for public sector at IBM Quantum. And when we think about quantum computing and quantum algorithms, I think there's been a lot of really exciting work that's come out of IBM, especially over the past few years, anchored in our vision for how the future of computing and kind of best-in-class computational capabilities, quantum or classical, can be brought to bear to solve the most pressing problems that face society today. So with that, I'll try and advance the slide. So one of the kind of anchor points that I want to use for our conversation today is that really the future of computing is heterogeneous. And there's a sense in which this has absolutely nothing to do with quantum computing. You know, we witness the rise of projects like the Colossus by xAI, we witness, Stargate with OpenAI, et cetera. And the future of computing, we have this notion that, oh, well, we have to be building these different kinds of AI infrastructures. We have classical HPC that we can be brought to bear on the problem. And then somehow there's this thing called quantum computing that slides into the scene there. More seriously, though, the plethora and explosion of new kinds of compute hardware suggests that how we think about designing algorithms to solve pressing problems and to develop applications needs to change. And in particular, it means that we need to be thinking about how we take the best of what a given compute capability can do and how we bring those best-in-class capabilities together to solve interesting problems and to solve them in novel ways. And so with that, on the quantum side of things, because this is a quantum, the quantum talk, just want to give a little shout out to some stuff that we're planning to build here over the coming years. So what this is an artist rendition of a data center in Poughkeepsie, New York, which is about maybe an hour from where I'm sitting right now. In the upper right of the figure, we see 4 IBM Quantum System 2s. These are freestanding modular quantum computing systems, very large dilution refrigerators that we're using to explore building out large-scale quantum computing infrastructure. On the left-hand side, towards the rear of the graphic, we see a rendition of IBM Quantum Starling. This is the first fault-tolerant quantum computer. We plan to develop this and have this available for our customers and clients to use by 2029. Given our current thinking on the architecture and what we know about quantum error correcting codes, we envision that Starling will be about 200 logical qubits and capable of executing about 100 million operations. Then later in the mid-2030s, we have IBM Quantum Blue Jay, left-hand side of the screen, closer to the foreground. There, we envision that being about 2,000 logical qubits and running about 1 billion quantum gates. These systems are not just simply artist renditions that are very beautiful. We have a roadmap. You can go Google that, IBM Quantum Roadmap 2025. We have a very credible plan of how we're going to de-risk the engineering of these large-scale quantum computing systems. And we remain fairly confident that we can achieve these milestones in the timeframes that we've set out. So we have this kind of hardware coming, and that's very exciting. And we have the kind of hardware that companies like IBM have put on the cloud today and that people can access through platforms like qBraid and et cetera, right? And so, when we think about developing new kinds of quantum algorithms to take advantage of this hardware, one of the things that we've really been excited about and working on for the past few years is how we can develop new quantum algorithms that are based on quantum and high-performance computing. And we are really taking a very bold stance that the combination of those two compute capabilities in particular should allow us to unlock quantum advantage by 2026. We have some reasons for that we'll get into, technical reasons in a couple of slides. The essential point is to recognize that quantum computers are really good at generating samples from probability distributions and doing other kinds of computations. But we also have decades and decades and decades of research on how you use high-performance computing to solve interesting computational problems. And there's a whole community of researchers out there who get up every day and they think about developing code for those systems. They think about developing new uses for those systems, et cetera. And so we want to partner with HPC providers in order to find new ways of developing quantum algorithms. And so shown on the bottom of this slide are just some examples of various papers around this notion that we've introduced called quantum-centric supercomputing. Now, Kenny sort of stole the thunder here, but that's okay, Kenny. So thank you for giving the shout out around this National Quantum Algorithm Center. So this is a partnership that we launched with the state of Illinois late last year to develop this algorithm center in the Illinois Quantum and Microelectronics Park, and to really develop new applications and algorithms, both for scientific use, also commercial use, et cetera. And so we're really excited to see the work that will come out of this algorithm center in the coming years. Now, one of the reasons why we're very interested in quantum and HPC is we've already done our own work showing how using these quantum-centric supercomputing approaches, we can get comparable and to best-in-class classical methods results from a quantum computer using an amount of time that is actually fairly modest. In this case, maybe about 2 hours of quantum compute time, whereas using this self-same problem in a fault-tolerant way would take about 13 days, or if you did something like VQE, it might even take 3 million years. And so we're really excited to see how all of these algorithms can come together, how we can tackle new kinds of problems, et cetera. And so we'll just close. Anyway, I guess everyone has a platform. We have a platform too, okay? It's based on the Qiskit SDK, the most popular developer kit. We have these Qiskit add-ons, which allow researchers to develop new capabilities and kind of tools that they can plug into their workflows. And we have Qiskit functions, various companies like QControl, Kedma, Algorithmic, et cetera, that provide application level capabilities that can be scaled and that leverage the best in class of what our ecosystem has. So with that, I will give the QR code for the IBM Quantum Platform and say that if you want access to the most performant quantum computers, go scan that QR code. Thanks.
Awesome. Thanks, Travis. Bob, do you want to go next?
Hey, everybody. My name is Bob Wold. I am the CEO and co-founder of Quantum Rings. Before I jump into it, I just want to honor what everybody else said. We have the leaders in QPU, the leaders in GPU, the leaders in bringing kind of students onto platforms and big companies onto platforms, all here talking. And in some ways, you might look at these things and think these things are competitive, but really these things are all kind of playing together in what's starting to become a really cool ecosystem. Where Quantum Rings plays in that ecosystem is we build developer tools that make quantum computing a lot more practical for enterprises to get started on today. And our leading tool is a very large-scale quantum simulation that lets you execute quantum circuits on classical hardware. And so to sort of set the stage for the conversation today in a little bit more of a corporate lens, it's been estimated that the economic value that's going to be created by quantum computing is going to be absolutely massive in the relatively near future. And this isn't coming from some overly optimistic quantum people. This particular estimate comes from McKinsey & Company. And we can see from a lot of information, including information put out by IBM, that 60% of Fortune 500 companies are actively exploring or are already engaging in quantum computing. We can also see from surveys put out by BCG and others that most of the people who start investing in a quantum computing program intend to maintain or increase their spending. But we can also see that almost everybody agrees that the current immaturity of quantum computing is blocking them from getting meaningful results. And so, well, a lot of what we talked about just recently was this really cool vision for how large quantum computers are going to be really soon. The current state is a lot harder for people to work in. The current state is that we see error rates between 0.1 and 1% per operation. The costs are very high. Actually, a fairly reasonably priced quantum computer will cost you as much for a second as a very high-end GPU will cost you per hour. And they're scarce. I ran a circuit just last week, and it took 12.5 hours of wait time to get access to that computer. And so if you are one of the developers working at an enterprise and you're trying to do this work, it can be pretty frustrating. Now, the cool thing is, the ecosystem is there for you, and Quantum Rings breaks a lot of these limitations. So the way developers work in any field is we sort of do these iterations. We design, we develop, we test, we learn, and the faster and the cheaper we can do those iterations, the quicker we get to innovative answers. But when you have to put a quantum computer into the mix in your development cycles, it's just way too slow and way too expensive. And so Quantum Rings lets you execute hundreds of qubits with millions of operations with low errors on your desktop or in your cloud. And we let you do that today on the reliable hardware that you have. And so one of, we have IBM here, one of the leaders in putting out educational material on quantum, along with all the other stuff that Travis highlighted. You can go to their website today and see an example of how to do a 127 qubit optimization problem, estimated to take 8 minutes on a QPU. You can run that in 30 minutes on your laptop with the Quantum Rings SDK and actually get a highly accurate answer that usually, it's probabilistic, but usually will actually give you a more accurate optimization. You can even go to more infamous things like Google's 2019 quantum supremacy experiment, estimated to take 10,000 years on the fastest supercomputer, and run that on your laptop in 2.5 days. Your laptop will turn into a space heater for 2.5 days, but it will get you the correct results. After we launched that, we partnered with NVIDIA, the company that Marwa is representing, and we launched full GPU support with CUDA-Q at GTC in 2025, and now you can do it in under an hour with an H100. We make this free for academic users, and we have packages for even small businesses, but even support the needs of large enterprises. And we've seen good adoption from hundreds of universities, thousands of users, millions of circuits executed. And what's even more exciting is we offer simulation today, but we're excited to announce to the QED-C folks here that we will be making a new offering available this fall called Open Quantum, where we aim to democratize quantum computing itself and provide an easy few line of code change to go from executing locally on your simulation onto quantum computers. And most interestingly, through a partnership, are going to be able to make a lot of this quantum compute time free in many cases. So check it out, join the waitlist. We'd love to email you and keep you up to date. So if you're just getting started on your journey, or if you want to enable your developers to go further, or if you've already got proof of concepts, but you want to scale them up a little further, let's talk. I'm Bob at quantumrings.com. Or if you're more of a do-it-yourself person, you can just go to quantumrings.com, sign up for free, and give it a shot. Thank you.
Thanks, Bob. Let's move towards the Q&A. So thanks everyone for the excellent talks, and this was really educational for me. I learned so much, all the exciting things that companies are doing in this space. So my first question, again, for this panel, I'll just ask questions and feel free to answer as you like. So my first question is, do you or your customers have a clear use cases for quantum computers? We have heard about several use cases during your talks, but you want to add on to some of the use cases that are not very well known? Or you think that there still needs to be a lot of exploration from domain experts to understand what are the potential applications?
Well, I can start. I think most of the user comes with really their use case that is interactable on classical computer. And one of these, of course, is one of the very active area is the quantum chemistry applications. And also optimization problem for combinatorial optimization problems, computational fluid dynamic problems. So at NVIDIA, most of user comes with those applications, and they are looking to run simulation at a scale that they start to see some useful or meaningful large applications where they can start to see like the value of quantum computing. And here we are using CUDA-Q GPU acceleration to run that. And we have been doing work with with JP Morgan, where they have been running simulation for QA with labs for up to 40 qubits with the GPU state vector simulator. Also, we have recently published also work with ANSYS and the Danish Center of AI, where they run simulation for computational fluid dynamics for up to 39 qubits. We also have work done for chemistry with BSF, where we also run a simulation for up to 60 qubit with tensor network. So I think most of users have they are aware of their applications that is interactable on classical, and we are helping them to scale this and see the benefit of the value on quantum.
Yeah, maybe I'll sort of just continue to expand on what Marwa said. So Marwa did a great job of picking a couple different like really valuable use cases from different industries. But maybe I'll sort of like zoom out just a layer and then say like, how does a company go from, hey, quantum computing is going to change the world into now I have a quantum computing program in the office of the CTO that's de-risking the technology for me. And usually it follows this journey uh, which you can sort of like infer from what Marwa described, where you start by saying, okay, let's go out and look across our lines of business and sort of survey what problems are currently running into the limits of computational capacity. Like, where are we actually computationally bound on problems? Now, not all of those problems are going to be solvable by quantum computers, but some subset of them generally are. And so then you take that giant list of problems, you intersect it with these algorithms, Swamit, that you highlighted at the opening of this, and you sort of say, okay, which types of these problems map into which types of these known algorithms? You create an inventory of your potential quantum impact. Now, once you do that, most companies will then sort of say, okay, well, are these problems worth de-risking? Do I just put this on the shelf, or do I actually hire one or two people and sort of scale down these problems into manageable, smaller versions of these problems and start applying those known algorithms to those problems? Some very advanced organizations are trying to also develop new algorithms or improve the algorithms, but I think a lot are trying to basically apply the known algorithms that have come out of academia and out of the national labs to the problems that they have. They'll usually do that in two different paths, though. So one is to say, can the algorithm actually solve that problem? And then the second is to say, okay, where are physical quantum computers at this point? Like, how far can a physical quantum computer take this? What are the resources that will be needed to do this problem at scale? And what are the resources that look like today? And I will say, this is an extremely exciting time to be in quantum computing because like we're on an amazing trajectory, but you also need to be like very aware of where we currently are so that you don't sort of overhype and get too excited about when that impact will impact your business.
Actually, Bob, if I may, I think there is a sense in which there's actually a pre-step to that notion of asking about the pressing computational problems, because at least in the experience that I've had working with some of the customers and clients of IBM, actually step one is just getting a handle on what are we as a business even trying to do? Where are we in some sort of digital transformation journey? Who are the people that have heard about quantum computing in the business, and what are they, how do we view it as a strategic competitive advantage for us, et cetera. So I think there's actually a step that you have to do before that, which is just anchoring quantum computing in a kind of business strategic context. Now that can go hand in hand with this, kind of inventorying of computational problems, et cetera. But I remember like working with a client on a project, and actually the vast majority of the battle was actually just getting a handle on like, what do you all care about, and what are you trying to do in this journey with us, and why is that significant for you? And then we worked out some interesting problems and came up with interesting projects. But I think business's step one is actually just asking like, why are we doing this? What is the strategic imperative for us? And then that helps inform some of these more technical conversations and the strategies around how you actually scope a project, et cetera. And then, Swami, if I may, I think that companies have gotten incredibly sophisticated. I've been with IBM for just over 7 years now. My first job was on a team doing delivery against research with customers and clients. And yeah, back when I got started, there was a whole heck of a lot of like, what is quantum computing and et cetera. And these days, I think customers are more sophisticated. They've worked with us, they've worked with other companies, et cetera, and they're getting a handle on the maturity and capability of the quantum computing industry as a whole. And so I think we're able to have a lot more nuanced conversations and a lot more thoughtful conversations and a lot more strategic and deep conversations. And we actually produce better work as a result when we think about how quantum computing is going to transform a given business or a given industry.
Excellent. Yeah. Thanks for all the insightful answers. My next question is more on the hardware. What type of hardware do we need to show this, first utility scale quantum computing? What are the right metrics to think about when we are thinking about hardware resources? Is it qubit counts, connectivity, gate fidelity, or maybe we need even, a higher level metric? I'm just curious how all of you are thinking about hardware.
So maybe I'll kick this one off. The thing that I want to instill first is, I think, yes to all of those metrics. Those are all extremely, extremely useful. But even taking a step back from like, what are the specific metrics? I think the hardware resources that we're going to need for true impact are kind of a constantly shifting target. So anybody that tells you that you're going to need 100 logical qubits to execute X or Y or Z for utility may not be telling you the entire truth. I mean, one thing that we've seen recently is that, you know, the number of physical qubits that you need to crack 2048-bit RSA encryption has dropped from an estimate of 20 million qubits to 1 million qubits over the course of, 6 years or so. So when you see progress that's happening that quickly, I think businesses should be careful about assigning too much weight to what the actual true resources that are needed are, and maybe trying to be a little bit more optimistic when it comes to those resources. In my opinion, like, I think we should expect the timetable to truly useful quantum computing to continue to accelerate as people are, you know, developing better and better quantum algorithms.
I couldn't agree more with what Kenny was saying. In fact, if I know it's a little bit off script, is it okay if I share screen again to share something from a DARPA?
Oh yeah, please go ahead.
Yeah, okay. So this is totally public information published as a part of the DARPA quantum benchmarking initiative. But I just love this chart. Like, this is like my spirit chart. I go to this for like every quantum conversation. But essentially, they put together this really cool scatter plot, which essentially shows all of these different, very well researched use cases. And they plotted them out. And on the horizontal axis, you have the number of logical qubits needed, or like that are currently understood to be needed for that. And on the vertical axis, they have essentially the number of operations that are needed in order to execute those at scale. And so, you know, we tend to think about getting hardware better and better, getting these error rates down, getting logical qubits with better error codes, and scaling the systems with heterogeneous architectures. And all those things are right, but that essentially moves this line that they kind of have indicated here with squigglies, right? It sort of like moves those lines. But as Kenny pointed out, these algorithms are constantly getting better. And so all of these dots are sort of like shifting down into the left also. So that particular red triangle right there is the one Kenny was just alluding to. That's RSA 2048. And, you know, this was published, I think, back in like February of last year. And now that dot doesn't live in the same place on this chart anymore. And so being aware that as we open quantum innovation to more and more people, not only are we going to see the hardware manufacturers continue on this amazing breakneck trajectory that they're on, but we're also going to see more and more software innovations that drive all of those algorithms down and to the left. And where I'm most excited is actually in the software enhancements, because if we look in the AI space, we can see things where, like, over the course of, say, like 7 years, we went from performance of this cool image recognition algorithm called AlexNet. It became 44 times more efficient and requires way less computational load simply by publishing the algorithms and getting more people working on them. If we can see that same type of thing in quantum, this could all start shifting very fast. People just need to have the ability to participate in that innovation, and they need to have the ability to test those things on real quantum computers and quantum simulation at scale.
I think the only thing I might add to this is that the conversation thus far has focused on, we have, you know, known algorithms, known applications. We're focused on simplifying those circuits, making them less complex, etc. And that's all well and good, and that's very interesting, right? And every time we can move things down into the left as hardware is advancing up into the right, that's a very beautiful world to live in. But one of the things I want to come back to from my remarks earlier is that we can also think about developing new kinds of quantum algorithms, you know, and we're very excited at IBM about these quantum and HPC algorithms. They go by the name of sample-based quantum diagonalization, SQD, derivatives thereof, etc. You know, and these represent new ways of thinking about how we work with quantum and classical compute resources to solve interesting problems. And so I will say there's a sense in which there's a lot of sort of greenfield available with today's hardware, where we can develop new algorithms. Maybe some of them are heuristic in nature, they're approximate. You know, we try and develop them in a way that have provable convergence guarantees, etc. You know, but the fact of the matter is, in my opinion, is that the hardware is already there. in terms of this impact, right? Now we can debate whether or not this is quantum advantage or quantum supremacy or blah, 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 right? But like the hardware is there, right? Like we can do thousands of 2-qubit gates on hundreds of qubits, and like it works, and you can get reliable results from hardware. The question now becomes, if we have that compute capability, how do we develop new algorithms that take advantage of it? And so in that sense, I think it's, this is a marketplace on algorithms. And we just need to really focus on not just how do we take algorithms that are already known and already studied and how do we simplify them, but how do we empower people to develop all new algorithms, which is one of the reasons why we're very excited about this National Quantum Algorithm Center in Illinois.
Perfect. That's a great segue to my next question. And that's, should we keep...
I think you know how I'm going to answer this.
Yeah.
Now.
Yep. Should we keep investing in NISQ algorithms, or should we just focus on fully fault-tolerant systems? And I think Travis alluded to, thinking about both. But yeah, I'm curious what others are thinking about.
I'll answer just very briefly because I feel like I've taken maybe more than my fair share of time and get input from the others here. But at the Quantum World Congress in Washington, D.C. last week, I was really excited by a lot of the roadmaps that were put forward. We essentially saw promises of 50 logical qubits this year from a couple different QPU manufacturers, with even some saying that by 2027 we might be in the high hundreds of logical qubits. And so if we really are talking about like 1 to 2 years before we have systems with hundreds of logical qubits, then I actually think time is best spent looking beyond NISQ. But I think that if you're in the weeds today and you're really looking to innovate, we have, functional quantum computers today, like Travis said, that are these kind of NISQ era quantum computers. And people I'm always blown away with the amazing stuff that's coming out of it. And all of that work that happens in the NISQ era, by the way, enables logical qubits too. Like a lot of those roadmaps about how we're going to get to all of those logical qubits make a lot of assumptions around what we're able to innovate on in the NISQ era.
I agree, and also I would like to add that I see also NISQ algorithm. It could be also a bridge to the fault tolerant. So algorithms like Krylov or quantum phase estimation, you always have to start from a state that has to have a strong overlap with the true ground state, and question always how we are going to prepare such a state. And so that's also where maybe simulation on noisy quantum hardware, like with VQE or QA, that might help for, like, especially for VQE for chemistry, can help to generate such a state that can be used for NISQ for algorithms like for Krylov or for quantum phase estimation. So I think it's also still could be a bridge to the fault tolerant quantum hardware.
Awesome. Yeah. I think this question was answered partly by the panelist. I think I'll briefly ask this question. If you have to pick among these sort of bottlenecks, algorithm design, mitigation or error correction, and I think integration with classical systems, what would be your top pick in terms of the biggest challenge that we see towards getting to a quantum utility? Like if you just have to pick one, maybe we can go around the room and quickly share our opinions.
I think I'll piggyback off of Travis's opinion that was expressed just a bit ago, which is that it's great to refine existing quantum algorithms, but what we truly need are new quantum algorithms. And so I would definitely highlight algorithm design as being the primary bottleneck here. And I think this is honestly being recognized by lots of major players. Obviously, we've talked about the National Quantum Algorithm Center a lot today. Kind of the whole point of that is to build a convergence of people who want to use algorithms and people who want to develop algorithms, with the goal of building new algorithms that can actually run on the quantum computers that we're going to have in potentially, 2 to 5 years or so. Without that, these quantum computers are just going to sit there and they're going to be giant investments that are completely useless. But willing to hear other people's opinions here.
I also agree with Kenny's bottleneck. The algorithm design here is a bottleneck. So most of algorithms that we have today is either theoretical or just tailored for an ideal quantum hardware. And so I think we need to develop much better algorithm design. So we are starting also now to explore how AI might help to design such quantum algorithms, because designing quantum algorithm also is not an easy task. And so we are starting some research on that area. So with Alan from Toronto and St. Jude, where we developed this generative quantum eigensolver, where now AI can be used to design such algorithms. And also with recent work we did with the QA-GPT, where we are using AI to generate quantum circuit that's going to be shallow circuit and optimum to be run on quantum hardware. So we are leveraging now AI for how can we use this to actually fix this and develop much better algorithms to be run on the next devices.
That's excellent. How about you, Travis?
I guess I have to agree with myself and say algorithm design.
Yeah. Yep.
I don't know how you guys can pick one. Like, and this list is such a like short list too for the whole universe of like awesome problems that we still need to solve. I think it has to be this confluence of sort of everything. You know what I mean? Like, I mean, we without error mitigation, you can't do most of these algorithms because we won't have systems with enough logical qubits. Without integration with classical, you know, we're not going to be able to do a lot of this. You know, Travis focused a lot on his roadmap around these heterogeneous architectures where, you know, we're not just making single QPUs bigger and bigger and more reliable, but we're building systems and we're abstracting different, you know, sort of roles and responsibilities and coordinating in these systems. There's so much good science and so much good engineering work that has to be done. And well, I do agree with the group that there's going to be so many more exciting algorithms that come out. I also am just extremely excited about the algorithms that we already know of. I mean, even at 100 logical qubits, I think we're going to be seeing billion-dollar, you know, problems being solved very quickly. And so, yeah, I'm just excited about all of it. I don't know how we could pick.
Yep. That's a great answer.
Can I add one thing to that list of bottlenecks that I don't know if we've talked about, and it's come up in some of the questions, because we do have a lot of people who are interested in knowing, how do I get into this field? Is talent a bottleneck? Do you all find it difficult to find people with the right skills? I'd like to, at some point during your conversation, and maybe that's later in the questions, touch upon that bottleneck as well.
Yeah, I think I saw Raul's question about this, and yeah, there's been a number of others as well, about, you know, whether you need a master's or a PhD to work in the quantum computing workforce, because quantum computing has this kind of idea that you've got to be extremely, extremely well educated and be very, very specific about what you've studied. This is not necessarily the case. I think that there's actually a lot of room for people who have even like bachelor's degrees to work in quantum computing. Just like any other workforce, there's going to be a need for people who are software developers, as long as AI doesn't take them all away. There's going to be a need for people who are actually maintaining all of the components that are associated with running these quantum computers. I'm sure maybe Travis, you could say more to that on what's required to actually upkeep one of these larger new IBM machines that are coming out. But overall, I do think there's probably not actually as much of a talent issue as we make there out to be. There's likely a lot of talent out there that could work in the quantum computing workforce with a small amount of upskilling.
Well, I agree with that statement, but I guess I'm curious, you all specifically, if you have a job posting for someone who's going to be working on algorithm development, is that a hard position to fill?
Algorithms development is a little bit more difficult to fill, for sure. I think that it's getting better and better as quantum computing is getting more popular and people are studying it in their bachelor's, master's, and PhDs. But yeah, it's certainly more difficult to fill than software developers.
Well, we actually.
Go ahead, Travis, please.
Okay. I mean, we have an interesting role in our organization of quantum algorithm engineer, and this is somebody who exists at the intersection of software and research, and very often these are people who are working with our customers and clients and supporting them in their own journey and their own projects, you know. And such a person, you know, doesn't necessarily need to have a PhD in any discipline, and you know, they obviously need to know something about software development and obviously need to know Qiskit working at IBM, you know. But I think to Kenny's point here, it's more a lack. It seems like it's more of a lack of awareness within these pre-existing fields of computer science and electrical engineering and etc., where people still think somehow you have to be a PhD physicist like me, right? And maybe it's just us physicists are so loath to let go of this technology, right? And to let everybody else in a way. Because I could see tremendous value in somebody who's, studied CS. If you know Python, you know how to program a quantum computer, right? Like, you know how to use the cloud and etc. You know how, you can do all sorts of really interesting things. I think it's more about those people realizing that quantum computing is increasingly accessible. We don't have to get sucked into these weird conversations about the spookiness of quantum physics, because quantum physics is a well-defined mathematical theory of the world. So therefore, it is intelligible to human beings. It's one of my biggest soapboxes, is this sort of mystique that we put around quantum physics. I think it does us a big disservice. And I think if more people were just aware that, yeah, there are these things like quantum algorithms engineers, or we have quantum software developers, or, we have people who are just working on AI for quantum and making the Qiskit code assistant better, etc. Right? Like there's these whole new personas are being unlocked within the industry, where you don't have to be a PhD in anything, much less study physics as an undergrad, in order to make a valuable contribution. So I'd say, to answer your question succinctly then, Celia, it seems that the bottleneck is more the lack of awareness, not so much a lack of availability of talent per se, right? And I think we as an industry could do a lot more to demystify, right? And I think the work, qBraid and others are doing, building interesting products and tools and services, Bob, your company too, right? That it makes quantum much more tangible and accessible to a wider class of people who can then see a viable and tangible path to a career in the industry.
Thank you. Well said.
Yeah, I will also sort of echo what Travis said. And I will also add sort of a geographical element to it, that even if you're trying to hire those like highly specialized roles, certain geographies have like a much higher density of those. For example, I live in colorful Colorado. It's a nice rainy day, so it's not as colorful today. But in this area, we have so many different quantum companies, like, really large quantum companies, that actually when we need to fill like a key quantum role, it doesn't tend to be that hard to find applicants. And so that's one of the reasons I think a lot of the work that's being done by like the EDA and the governments to try to sort of establish these different local clusters of talent are extremely exciting, whether that's, Colorado, Chicago, the Atlantic kind of consortium. They all do a great job of sort of creating these clusters, these hotspots for quantum. And if you have a company there, it's a lot easier.
Awesome. Yeah. Thanks for asking this question, Cecilia. This is really important. That's what we do as universities. We teach undergraduate and graduate courses. So we are also trying to ramp up the curriculum on quantum computing. We want to involve more computer scientists and electrical engineers, as Travis said. They play a really crucial role. Thank you, everyone. Thanks for joining this webinar. Let me check. We have 2 minutes, maybe, if we can get one of the
I'm going to hijack the 2 minutes, because
Okay,
I'm going to tell a
sure.
story that I think is sort of illustrative of this field. And some of you have heard me tell this story before, but we've got, I guess, a few people still on the line. I had the privilege of having a dinner when I was visiting up in Cambridge with Peter Shor and others at MIT, and we were going around introducing ourselves. And Peter Shor said, I'm Peter Shor. I discovered an algorithm for factoring large numbers. And of course, we all knew who Peter Shor was, but what struck me in the way he presented himself was that he discovered this algorithm. Like it was out there like a planet waiting to be discovered. And that what we need as a community is more explorers, more people out there. And this is sort of why I asked the question about talent. I think there are a lot of people who, if they are inspired, will be excited to go out and explore for algorithms in this space. We just need them, as I think someone said, to be more aware. I think Travis used that word. And so you too out there can be a Peter Shor of the future if you go out exploring for algorithms that take advantage of quantum hardware. And it isn't, a quantum computer scientist is not identical, exactly the same as a regular computer scientist. So it's on the educators, Swami, you and others, to help on the education end so that people recognize that there's a big world to explore in this space. So I want to thank everybody who, and there's some comments going into the chat here. Maybe others have some similar views, but thank you all for participating, and look forward to seeing progress by you all and others in the quantum algorithm space.